Alrighty, we're live. Hello, everyone. I am Verde Arbusto. This is the Schumann Resonance channel on Facebook and on YouTube and parts beyond. I want to thank you all for being here. It's Sunday, November the 1st. It's the day after the sacred holiday of Halloween, All Hallows Eve. I had a great time. It was a great live cast last night, and I appreciate everyone for being there. We were talking about HARP and CERN, but mostly HARP, high frequency aural array program. All right, so atmospheric heater is what a HARP is. All right, all right, so onward and upward. I got this. I wanted to do a short video. I wanted to present this to you. It was a fascinating article that I got in my email today, and the title, the heading, I just couldn't resist this: "Rocks that crackle and sparkle and glow, strange pre-earthquake phenomena." The general topic is earthquakes and the precursors to earthquakes. Okay. There are a number of factors that come in to play before an earthquake that you actually can predict. And a lot of people, my regulars, my subscribers, people I care about, we talk about animal behavior before earthquakes. And people will get oddball symptoms that they don't know where they're from as well, from the precursors of earthquakes. Okay. So this is where we're at today. Okay. So I think first I would like to say that I present these articles, these scholarly articles, not in their totality, but as an introduction. And I hopefully provide enough that you may feel satisfied that you got the article. Okay. I bring up what's relevant. This one here at 35 pages, there's no possible way I'm going through all of it. And also because I don't understand all of it. And a lot of these, you learn. These scholarly articles are here to inform you. So it would be truly unique that if you read these and you knew everything. No, that's not how it works. So we're looking at these things. I've brought up a number of them so far. I have either made videos of them or I've made posts. I put them on Facebook, and I put them up when I find things that are relevant to our discussion of understanding what's going on in the world around us. It's my personal belief that people came here, that if you are here on this planet, it's the number one reason for being here on Earth is to actually learn about the planet, in my humble view. We're not on Mars or the moon. Seems absurd to say, oh, well, yeah, we're not on Mars, but we're not having this conversation on Mars. And there's this idea, this is sort of off the mark, but there's this idea that humans are going to go off into outer space and that somehow we'll find a planet that's better for us than Earth. And of course, any reasonable person would say, if you can't make it work on Earth, you're not ever going to find any better place. Earth is a planet where you can be lazy and get away with it. Other planets, you can't be lazy, meaning there is no waste in the rest of the universe. You can't make as much of a mess elsewhere in the universe as the humans have here and get away with it and not only survive but thrive. Human is a place where, the Earth is a place where people can go and be messed up individuals and do messed up things. And because the Earth is so prevalent in life, and is so forgiving, the planet Earth is so forgiving that we are allowed to mess up and not pay a heavy toll, as in complete and total annihilation. Okay, so that is as a precursor. I'm saying that relative to this article here, I am saying that it is, in my view, the purpose of all people in their awakening. If you're a sleeping individual, if you're a total turd, no, you're just here because you failed out of all the other lifetimes, and you're here as a failure. Like, okay, but if you as a person, in my humble view, are here on the ascension and we are evolving track, then it is important for you to understand about what's going on the earth, in the earth, and if you can, how that affects you and other people. Okay, so this is one of those articles that is for the purpose of us, I think, discovering the wonderful characteristics, the wonderful qualities of this planet. Right. And so this was an article that had really piqued my interest, and I thought I would present this to you all so you could get something out of it. Okay, so, all right, let me get into this here. Okay, so the name of this is Rocks That Crackle and Sparkling Glow. This is from the Journal of Scientific Exploration, Strange Pre-Earthquake Phenomena by Friedemann T. Freund. Freund. I know I butchered that name. All right. All right. Abstract. Seismic waves are the most dramatic and most intensely studied manifestations of earthquakes. However, we also know of non-seismic phenomena which precede large earthquakes. Some of them have been reported for centuries, even millennia. The list is long and diverse: bulging of the Earth's surface, changing well water levels, ground-hugging fog, low-frequency electromagnetic emissions, earthquake lights from ridges and mountaintops, magnetic field anomalies up to 0.05% of the Earth's dipole field, temperature anomalies by several degrees over wide areas as seen in satellite images, changes in the plasma density of the ionosphere, and strange animal behavior. Because it seems nearly impossible to imagine that such diverse phenomena could have a common physical cause, there is great confusion and even greater controversy. This explains why reports on non-seismic pre-earthquake phenomena are regarded with suspicion in the scientific community. This may change with the recent discovery that igneous and metamorphic rocks, which make up a major portion of the Earth's crust, contain electric charge carriers which have been overlooked in the past. These charge carriers are defect electrons in the valence band, i.e. positive holes. Under normal conditions, they are dormant, but when they, quote, wake up, unquote, the rocks begin to sparkle and glow. This paper describes the physical and chemical nature of these positive holes, how they are introduced into minerals and rocks, and how they become activated. Evidence will be presented that once the positive holes are generated, currents propagate through the rocks, leading to electromagnetic emissions, to positive surface potentials, to corona discharges, to positive ion emissions, and to mid-infrared radiation. These phenomena are expressions of the same fundamental process, the, quote, awakening, unquote, of dormant positive hole change carriers that turn rocks momentarily into P-type semiconductors. All right, so right here, I'm going to draw your attention to this word, the awakening. Awakening of dormant positive change carriers that turn rocks into momentary P-type semiconductors. All right, I'm going to let that kind of sink in for a minute as you think about that. The awakening of dormant positive charge carriers. So, as they're getting hit by low frequency EMF um, emissions, the rocks awaken. Okay. I think what I'm going to do is I'm at like the 10-minute mark right now. I don't want to go into a lot of detail about this. I'm going to. There's a few paragraphs in here I want to kind of point out. Here's one: electric charges in rocks. Where do they come from? Several of the pre-earthquake phenomena listed at the beginning of this paper require a sine qua non condition: large electric currents flowing in the ground. Examples are local magnetic field anomalies and low-frequency electromagnetic EM emissions, both of which have been documented beyond reasonable doubt prior to a number of well-studied earthquakes. And they give some examples of studies here. When local magnetic field anomalies occur during the weeks or days prior to a seismic event, they require electric currents of considerable magnitude. Obviously, these currents did not flow before. Their generation is linked to the earthquake preparation process, but how this process works has remained a mystery. Likewise, if EM, electromagnetic emissions, are recorded from an area where an earthquake will occur, electric currents are required that vary with time. Given the suspected linkage between the observed signals and the inferred currents, we postulate that the generation of the electric currents is linked to the mechanical processes at depth when rocks are subjected to ever-increasing stress, causing dislocations to form and move. For decades, the attention of many researchers who take an interest in pre-earthquake phenomena has indeed focused on the generation of electric currents in the Earth's crust. Of all processes that have been discussed, two candidates have emerged with a physically well-understood mechanism of charge generation and separation. These are piezoelectricity and streaming potentials. Piezoelectricity describes a fundamental property of certain crystals that belong to non-centrosymmetric symmetry classes. That's Bishop in 81, Finkelstein 73. Of all naturally occurring rock-forming minerals, only quartz falls into this category. Quartz crystals, when squeezed in certain crystallographic directions, that's a mouthful, generate plus or minus voltages on opposite surfaces due to minute displacements of their ions relative to each other along a polar axis. Within the validity of Hooke's law, i.e., within the range of elastic responses, the voltages are proportional to the applied stress. When the stresses are high, the voltages generated can be large enough to draw sparks. This finds applications in household appliances, for instance, in the ignition of gas-burning stoves. Conversely, if voltages are applied to quartz plates cut along certain crystallographic directions via electrodes deposited on opposite faces, the crystals change their dimension. They become thinner or thicker depending upon the polarity of the applied electric force. This finds application in electronic devices such as quartz clocks, where the frequency of the applied electric field is tuned to the thickness of the quartz plates, so that the quartz crystals go into resonant oscillations. In rocks, such as granite, which contain a high percentage of quartz, the application of stress will of course lead to piezoelectric voltages on each individual quartz crystal. If the crystals are randomly oriented, which they normally are in batholiths, bathylitic rocks, the local piezoelectric voltages will cancel so that no long-range electric field is generated. Okay. Streaming potentials describe the fact that when fluids forcibly move through narrow openings and long capillaries of a porous body, there are always some electric charges, which absorb on the walls of the flow channels. The fluid retains charges of opposite sign to those that have been absorbed in the walls. As it moves on, charge separation takes place. In highly insulating fluids such as transformer oil or aircraft fuel, which are pumped through long, narrow conduits, streaming potentials can generate very high voltages that can cause sparks with disastrous consequences. So what they're telling you is aircraft fuel, which is very volatile, high what the heck do they call it? Octane. Yes, that's it. So high octane. Okay. So it doesn't take much to set it off. And what it's talking about, highly insulating. Okay. So it doesn't give out the charge. Insulating means it holds the charge in. So as it's flowing down, as the highly volatile jet fuel is flowing down the narrow corridor, it creates an electrical potential which generates sparks. So this is one of the reasons why fueling and unfueling jets can be such an extremely dangerous thing, an operation. Okay. In natural systems, in porous rocks through which water or brines forcibly flow along a pressure gradient, the voltages that build up as a result of streaming potentials are limited by the inherent ionic conductivity. At concentrations of dissolved salts, as commonly encountered in aqueous pore fluids, the maximum voltages may be as low as a few millivolts over distances as large as a kilometer. All right, so it can concentrations of dissolved salt. Salt is a carrier, so it can transfer a small electric charge over a long distance. Okay, that's basically what it's saying. Even though simple laws of physics limit the usefulness of piezoelectricity and streaming potentials as a mechanism to generate large currents in the ground, both processes have been widely invoked to explain EM emissions and magnetic anomalies before earthquakes. Unfortunately, neither piezoelectricity nor streaming potentials stand up to scrutiny unless boundary conditions are allowed to exist, which are generally thought to be quite unrealistic. Therefore, some other processes have to be considered, such as Tribo Electricity. Oh, that's interesting. Tribo Electricity, which is loosely used to describe any form of electrification during fracture. Okay. With the references given. Thus, we are faced with a conundrum. There seems to be no bona fide physical processes by which electric currents, i.e., currents of sufficient magnitude, could be generated in crustal rocks. All right, so this is where we're starting to get to the fun point. Okay, electrical conductivity of rocks. All right. Electrical conductivity of rocks. Okay, yeah, we're back. All right. At this point, it is advisable to revisit the question of electrical conductivity of minerals and rocks. Oxide and silicate minerals that make up the bulk of the igneous and high-grade metamorphic rocks in the Earth's crust are mostly good insulators, except for sulfide minerals, which are often quite conductive. The only oxide mineral that shows an appreciable electronic conductivity is magnetite, that is Fe3O4. In magnetite, Fe2+ and Fe3+ alternate, on neighboring sites, allowing for Fe2 and Fe3 valency fluctuations to delocalize over the Cation sublattice and to thus conduct electricity. So you have ions and then there's cations. So they're basically, it's a positive and a negative state, I think. That's the best way to put it. You have positive, negative, and neutral charges. So I think a cation is a neutral, if I'm not mistaken. I forget, it's one of those. Sublattice and to conduct electricity. All right, so when the valence is basically, it's a shell. You need 8 atoms, I think it's an atom, to form a valence shell. Why a valence shell on electrons, all right, how do I say this? A valence shell, I think you have, I'm going to have to look this up and explain, so I can explain it better, but you have 8, this is from my high school chemistry, I'm remembering this. Valence shell, I remember you need 8. Okay, so there are minerals, there are molecules that are stable. I'm going to look this up. Actually, hold on. All right, I am going to look up valence shells. I'm going to look up a valence shell. While I'm doing that, I'm going to play some music. There's my email. Hello. Okay, so I'm going to read this. You're going to show me reading it. All right. So it says, in chemistry and physics, all right, in chemistry and physics, a valence electron is an outer shell electron that is associated with an atom and that can participate in the formation of a chemical bond if the outer shell is not closed. In a single covalent bond, both atoms in the bond contribute one valence electron in order to form a shared pair. All right. So this is a covalent bonding. So all 8 spaces are taken up. Okay. All right. So this is stable. And I'm not sure, I couldn't tell you by looking at this what this molecule is, what this would be here. It's C1H4. I'm not sure what that is, but you have one, you have the C is 1, H is 4. You have 4 parts of the hydrogen to 1 part carbon. I'm trying to keep this the basic way that I can, or that I know how to explain it. The presence of valence electrons can determine the element's chemical properties, such as its valence, whether it may bond with other elements, and if so, how readily and how many. In this way, a given element's reactivity is highly dependent upon its electronic configuration. For a main group element, okay, a valence electron can exist only in the outermost electron shell. For a transition metal, a valence electron can also be an inner shell. Okay. That gives us a basic understanding of what the valence is, that it's basically this chemical bond that's formed where you need 8 spaces. An electron and a neutron, if I'm not mistaken. All right. Okay. So when we're talking about these here minerals with the ions, this is what we're talking about. That the valency fluctuation. So it is not stable, and because it's a valency, as it were, a valency fluctuation, it means it's not stable. And so when an electric charge comes in, it can activate it. Okay. And what they're talking about, the transition metals in your body are sort of the same thing, that an incoming charge will cause those to deposition. So move from one, they move, basically. It's not stable. They move from one part, a low, how is it? I think it's a low electric charge to a higher electric charge, I think, or higher to a lower state, whatever. I forget how it works in the body. But those are the transition metals. And it works the same thing that metals that are, copper is like that. It's a good conductor of electricity because it's inherently unstable. It's missing some of the ions there. It's not a covalent bonding. Okay. All other, back to the reading, conduct electricity. All other rock-forming minerals, including silicate minerals that are rich in transition metals and different oxidation states, are non-conductors. If the minerals do not conduct electricity, the rocks, which they form, must also be considered good insulators, at least as long as they are dry. There are only a limited number of publications on the electrical conductivity of minerals and rocks coming from a relatively small group of dedicated researchers who have built their careers around such laboratory measurements. That's interesting. They have determined that the only significant electrical conductivity in minerals and rocks is caused by ionic conductivity. For ions to contribute to the transport mechanism, however, high temperatures are needed. For instance, in MgO, which can serve as a model, ionic conductivity is determined by this magnesium, Mg2 plus cations, hopping into Mg2 vacancies. And thus, in this process sets in around 700 degrees centigrade. In olivine, which is Mg and Fe2, SiO4, that's silicon, the onset of conductivity is placed between 700 and 800 centigrade. Any conductivity below this temperature range is thought to be due to adventitious dirt or to mysterious carbon films on the surface of samples. All right, so you getting this? They're saying that it couldn't have happened any other way than dirt or mysterious carbon films. Okay, so they're a miracle. It's not happening because it's something unexplainable. Likewise, for rocks, conductivity is believed to be essentially nil until the temperature reaches high enough values to lead to partial melting, at least along the grain boundaries. Once partial melt forms, with or without participation of water, ionic conductivity becomes great. If enhanced conductivity is observed at lower temperatures, it is dismissed as being due to either insufficient drying or to intergranular carbon films. Okay. Given that this published information comes from respected laboratories where the electrical conductivity of minerals and rocks has been routinely measured for decades, those in the geoscience community who try to understand earthquake-related electrical phenomena were faced with a dilemma. Based on the reported laboratory results of electrical measurements, no mechanism seemed to exist that could account for the generation of those large currents in the Earth's crust, which are needed to explain the strong EM signals and magnetic anomalies that have been documented before some earthquakes. Therefore, the only available alternatives were piezoelectric effects and streaming potentials. However, as most researchers acknowledged upon closer scrutiny, electricity and streaming potentials are inadequate in more than one respect to generate large currents in crustal rocks. This led to an irreconcilable conflict between field observations and our capacity to provide a physically meaningful and substantiated explanation. Unfortunately, when a set of observations cannot be explained within the framework of existing knowledge, the tendency is not to believe the observation. Therefore, a general malaise has taken root in the geophysical community when it comes to the many reported non-seismic and non-geodesic pre-earthquake phenomena. All right. So what they're saying is when these scientists can't fit the facts into their framework, their model, they just don't believe what they're seeing. Okay? The tendency is not to believe the observation. All right. So that's part of the problem here of not believing what you're seeing and not being able to scientifically adduce these real world phenomena, these things that actually happen with the scientific mathematical models that say what's supposed to happen. I mean, to me, obviously, the model is wrong if it's not able to account for what you're actually physically seeing. So that's what this is talking about. All right. So I'm not going to read the whole thing. What I'm going to do is, like what I like doing is I'm going to kind of play music in the background and scroll through this just so you can get a sense of it. This video is kind of at like 30 minutes right now. And let me pause. Okay, I think we're back. All right, so I'm going to scroll through it. I'm going to scroll through this while the music's playing in the background. That way you can look at this. I don't have to read it. right, I'm back. Okay, so the video's at 35 minutes. I really gotta close it out. All right, and there's just too much for me to keep going on. All right, so I'm showing some of these kind of the graphics that they have, because this is kind of interesting to watch. And this was the one that I had put on the front. And I would really suggest that people go over and read this, except it's so long, you can't really, if you don't have time to read stuff, you really couldn't read this, even if you understood much of it. All right. So the takeaway from this is one of the things that I had read of the bad science, of them kind of destroying the sample to figure out how it actually works, right? And this is a common thing. Rupert Sheldrake talks about this, of in order to figure out the constituent elements of life, they kill it, grind it up, chop it up, and then put it in a spectrum analyzer. Okay. So there is there's a fine line between science, what science can prove, and them trying to outprove what is actually there. So them coming up with a model of, hardcore science, coming up with a model that does not take into consideration all of the observations, and more to the point, actually dismisses what you're saying because it doesn't fit into the model. Okay. So it's part of what this article is saying. That's why I thought this was a really good article. It's not just about the sparkling and crackling rocks, but there is also a correlation between those sparkling and crackling rocks to the sparkling and crackling that might happen in the ololiths, or the crystals that are in your inner ear. All right. And so if you've followed along with me to this point, you've endured the 40 minutes of this video, like I'm gonna consolidate it with saying that this also has to do with the ringing in the ears that people hear. The ringing and the vertigo is because of the piezoelectric effect. All right. Okay, so there's a lot more to really talk about, and I'm kind of lost in everything I want to say, and I want to keep this basic and sort of general, but also very relevant to people. So if you've been here the whole 43 minutes or whatever this video is, I appreciate it. Thank you very much. Thank you all for being here. I appreciate the comments, the love, the support. Thank you all for being here. I appreciate you coming around. And on that cheery note, I'm going to say have a great day, namaste, and I will see you on the next video, and maybe hopefully at the next live stream. Thank you very much. Have a great rest of your day. Bye.